We're going to start off with George. And George has been working in the addiction field for a long, long time. He knows the whole area, so he's a great person to start. And he will be talking about really the roles of stress and the dark side in addiction processes. Okay. And so welcome, George. I think we'll go on.
Okay.
Ask him questions.
Don't you dare. Okay, so what I'm going to do in this first lecture is lay out a broad sweep of conceptual framework and throw in some data to support this overall hypothesis. So my bottom lines are up here. This is the flow of the talk. The first part is going to be really fairly rudimentary, so it's kind of like from the sublime to the ridiculous. But I want to give you a framework for addiction that I hope will be useful for the rest of the course. And you can judge yourselves whether it's useful or not. So I'm going to take you through the conceptual framework, show you some animal data that supports it. I'm going to talk about 3 stages of the addiction cycle: the Binge-Intoxication Stage, the Withdrawal-Negative affect stage, and the Preoccupation Anticipation stage. I'll explain all those. I'm going to talk about gross brain circuitry that's involved in those stages of the addiction process. And then at the end, I'll just touch on a little bit of allostatic view of addiction. And that is not, I had a very prominent scientist introduce me about 15 years ago and announced that my talk was the allosteric view of addiction. I wish it was, because Changeur discovered allosterism or so forth years ago, and I would like to take claim for that, but unfortunately I had nothing to do with it. So this is a slide I just put together not too long ago. I've been working with Denise Kandel and Nora Volkoff and Ruben Baylor from NIH to revise a chapter we wrote on the psychopathology of addiction for a psychiatric textbook. And Denise Kandel is the master of digging through the literature and pulling out statistics that I think are very meaningful. And so I don't want to spend a lot of time on this, but this I actually waded through, and I spent hours and hours and hours on this, and you're welcome to try it yourself, but I waded through the National Survey on Drug Use and Health and verified every one of these numbers up here. So one column is the percent of the population, the US population, that ever used the drugs. And you can see that a lot of people have used tobacco and alcohol, right? And smoked cigarettes. But it and cannabis, but it kind of drops off from there. And if you look at heroin, it's a pretty small percentage of the population ever used it, right? If you go to last year use, you get similar figures. But then you can use that percent of last year use, that's kind of like current users who've ever used, and you can get a measure of how many of those met the criterion for dependence with DSM-4, which was a diagnosis of called substance dependence, and it's just been replaced by DSM-5, which is now a diagnosis of substance use disorders. And again, I don't want to spend my talk on this, but what they did between DSM-4 and DSM-5, and Denise does a very nice job in our chapter of explaining this, is they basically added the abuse criteria in with the dependence criteria. And now it's graded, so you can be mild, moderate, severe. And they took out one criteria, which was growing marijuana in your backyard is no longer a criterion for addiction or substance use disorder. So the legal part was jettisoned. And they added one, which is craving, whatever that is. We'll talk about that. Anyway.
Can I stop here for 1 second? Does everyone know what the DSM is?
It's the Diagnostic and Statistical Manual of the American Psychiatric Association, and it's used to categorize people with mental disorders in the United States if they want the insurance company to pay for them. All right? That's the bottom line. And the other column, though, if you look at it carefully, you can see some interesting things, which is that cannabis is higher than alcohol for dependence in those who have ever used or used in the last year. Alcohol is actually one of the lowest, but that's, of course, because the denominator is so large. Most people have drunk some alcohol, including most of you last night, but you're not alcoholics. On the other hand, heroin, of course, is the leader. with 57% of those who ever used, which tells you something about opiates, which I often tell lay audiences that old word hooked is a very real word when it comes to opiates. It's not a joke. So we'll talk about that later, maybe, maybe not. Anyway, I'm going to start moving through my slides. I just wanted to give you a flavor of the feet upon what, the floor upon which we're standing is shifting. And it's going to be a real challenge for drug abuse researchers to incorporate substance use disorders and that framework into what we do. And so I don't think the dependence category is going to just disappear, poof, because somebody in the American Psychiatric Association decided that. And the other thing to remember is those criteria were made by a committee, not by Moses handed down on a tablet from Mount whatever, all right?
And
Okay.
I think that's indicative of the fact that there's so much still unknown about the basis of addictive disorders, right?
Right.
And psychiatric disorders in general, so that the best the field can do, apparently, is to put a committee in a hotel someplace.
Yeah, and the committee was also, never mind, I won't say anything about the committee. Yeah, Anto.
Maybe George, it would be worth for them to mention what Tom Insel said just a few months ago, the director of NIMH, regarding the validity of the DSM-5,
Yeah.
so that they get the full picture, since we're starting this conversation.
Yeah, so Insel argued that that he doesn't want his researchers using DSM-5, he wants them to use DSM-4, that's the bottom line, right? So, but he's a little controversial, okay, just so you know.
How often do they revise it?
About every 10 to 15 years. This is the first major revision in a long time, yeah.
And what was the basis of him making that statement?
Sorry?
What was the basis of him making
Well,
that
he's not,
statement?
I think he's not very happy with the way they split up some of the disorders, and some have proliferated, so forth.
So,
I mean, Anton, you may know more than I do, because I haven't read all the details, so
actually,
just say
because
something.
I was inside NIH, so I've seen this a little bit more. So basically, in a nutshell, some psychiatrists are challenging the construction of a diagnosis based on those criteria versus based on functional changes, right? So if you were to forget that you had a DSM, 1, 2, 3, or 5, you say, okay, now why don't we give a diagnosis of something, a dementia or schizophrenia, based on a functional change or a functional impairment based on anatomy, MRI, and whatnot. And if you use that criterion as opposed to these symptoms-based criteria, then everything changes. Then the grouping and splitting of certain diseases changes dramatically. So there is a strong movement now, starting actually from NIMH, where they are proposing to recategorize many diseases in psychiatry based on functional criteria as opposed to observational symptoms or signs. So that's the story.
Yeah, and in our field, it's really going to be tricky, because I was at the, Anto was there too, I was at the Research Society on Alcoholism meeting and was talking to some of the people that have been involved in this from other countries. I'm thinking particularly of the chap from Australia, and John Saunders, and when I asked him, and I also flew back home with Mark Shuckett, who was on the committee for DSM-5 for addictions, and when I asked him, well, okay, where's the cutoff for addiction, okay, which is the definition I have up here on the board, my definition, it's a personal one. So where's the cutoff? And you get something like, well, maybe between 4 and 6. So you guys should ask Barbara that this afternoon, and you'll get a different answer, all right, about what is the cutoff. But actually, it's going to be interesting, because actually if you meet 2 of the criteria, you would be addicted. So any one of you, if you think about that, think about this hard, any one of you who took pain meds for any chronic condition, even surgery, would meet 2 of the criteria, right? So you'd be tolerant, I can guarantee it, and you would go through withdrawal when you stop taking the pen meds. I can guarantee that too. I can't tell you how many neurologists have actually called me up and said, I think I'm addicted. They weren't addicted, they just needed to taper. So, but they fixed that in DSM-4. They put an asterisk that said if it's for pain meds, you can't be considered meeting the criterion for substance use disorders. But what about alcohol? You know, you guys drink 3 or 4 glasses of wine this week every night, you're going to feel some tolerance by the end of the week. And when you go home and you don't have free access to alcohol, you're going to go through a little bit of withdrawal. You're going to have a bit of a hangover. Are you going to be substance use disorder criteria meeting? I don't know. Anyway, I need to stop on that or we'll never get through my talk. So, addiction can be defined as a chronically relapsing disorder that is characterized by compulsion to seek and take drugs or stimulus, loss of control in limiting intake, and emergence of a negative emotional state during withdrawal. And everything in the first part of that definition, most everybody that you're going to hear this week are going to agree with. Where you're going to get some controversy is the emergence of a negative emotional state. And this is one of my passions, and I've been spending a lot of time on working on this in the last 15 years. There's a lot of good reasons for it. If we have time, I'll tell you the story of how I ever came to that conclusion, because I was a reward kind of guy for a long time. So these are my bottom lines. I'm going to argue, and I'm not going to spend a lot of time on this piece, but because others are going to cover this in great detail during the course of your week. But addiction is an incentive salience disorder, and I'll explain that in a minute or two. It's also a reward deficit disorder. My main argument is going to be throughout my talks that it's a stress surfeit disorder. And I'm going to start talking a little bit about, and you'll probably hear more from others, that it's also an executive function disorder. And my theme is going to be that stress plays a role in all of these aspects of the addiction process. So there's not only a key element of stress in addiction, but I'm going to argue that it probably interfaces, albeit a little bit more mildly, but probably importantly with all the stages. Now, how did I get there from here? Well, it really has to do with a course I've been teaching at the University of California, San Diego, for 30 years, and another course that I started about 15 years ago. So I teach 450 undergraduates every year, drugs, addiction and mental disorders, and then the second course is called impulse control disorders. And when I got into developing the impulse control disorder course, I realized some very strong similarities between what the American Society of Addiction Medicine calls the process addictions and what we call drug addictions. Now, process addiction is pathological gambling, right? Which is, by the way, in the substance use disorder category in DSM-5. But you can take it all the way to compulsive sex, and I don't have to expound on that with what's been in the news lately. Think Tiger Woods, Anthony Weiner, the mayor of San Diego, and if you're Italian, you can go to Berlusconi, all right? So, but impulse control disorders, classically, were disorders. The archetypal syndrome is in fact, kleptomania, all right? So the person goes into the store, the classic case history is they go into the supermarket, and the tension is building, and they're sweating, and they're very excited, and arousal is very high. And they find their way to the aisle where they sell lobster cans, and they steal the lobster cans, and they stuff them in the pockets of their trench coat. And the tension now is enormous. And they exit the store, and there's this huge feeling of relief and pleasure, and they did it again. And they get in their car, and they drive home, and they throw the lobster cans in the closet because they don't eat seafood, right? That's kleptomania. It's all in the excitement, all in the risk-taking. On the other hand, a compulsive disorder, which is the red circle up there, think obsessive-compulsive disorder. Think the movie As Good as It Gets with Jack Nicholson. Nobody does psychopathology better than Jack Nicholson, all right? So in that movie, you'll remember he has obsessions of fear of contamination, fear of harm. He generates an enormous amount of anxiety and stress, and he engages in a lot of behaviors to eliminate those negative feelings. Like he had 12 locks on the door. He washed his hands every time with a new bar of Neutrogena. I don't know whether you've bought a Neutrogena bar recently, but they're expensive, right? So you collapse those two constructs, impulsivity, compulsivity, impulse control disorders, compulsive disorders, and you basically get the addiction cycle, which is my circle up there. And my argument is going to be that there are two sources of reinforcement that impact on that cycle, and that it gets worse over time. Now, when I first drew that, it was a spiral. But I stopped the spiral in my slides because people kept saying it looked like a toilet. And then some graduate student at Society for Neuroscience about 4 years ago mounted my spiral on a toilet, and that was his slide. And that was it. No more toilets. This brings up a thing I was preaching to the table last night. I'm going to preach to all of you right now. There are two sources of reinforcement in the addiction process, two primary sources, and then these can become secondary sources of reinforcement. Obviously, you all know what positive reinforcement is. I don't have to spend any time on that. Negative reinforcement, though, is a construct that's often misunderstood, even by very prominent people. And it basically means that you're removing an aversive stimulus, and that removal increases the probability of a response. And as I said to the table last night, if you're skiing at, 12,000 feet at Keystone Mountain and it's bitter cold and your fingers are getting numb and they hurt, you go into the warming hut and you warm them up. And that's a phenomenon that cold, that aversive stimulus, that hurting fingers increases the probability that you're going to increase the frequency of times in the warming hut, the length of time in the warming hut, the latency to go to the warming hut, et cetera, all right? That's negative reinforcement in a nutshell. Does it feel good? Absolutely. Does it release dopamine? Very, very likely, okay? So that's our addiction cycle. These are the DSM-4 criteria.
Quick question about that.
Yeah.
So then, would you just say, most of us might think, okay, well, negative reinforcement is actually punishment, and that's a line you're drawing. So what do you call punishment?
Punishment is defined in psychology as any stimulus that decreases the probability of response. So that's a critically important question you just asked. Punishers don't work. That's why they're not used in school anymore. Does anybody know why? Why isn't punishment used in education anymore? Why don't you just zap the kid every time he doesn't learn his math tables? Or why, when a kid is wandering around sticking a fork in the electrical outlet, why don't you zap them then? Well, because punishment doesn't work. There's a rebound phenomenon after you remove the contingency of increased behavior toward the stimulus. And it's very well documented in behaviorism and basic psychology, okay? But a lot of people, you're right, a lot of people mix up this. Remember here, this is an increase in the probability of response, not a decrease. So punishment works great if you're suppressing the behavior and the contingency is in effect. And when you start talking about treatment later this week, you're going to find out that there are punishing treatments for addiction. Antabuse is a classic example. If you take Antabuse, that's disulfiram, and you drink alcohol, you're going to get sick. And it works great. But what's the problem with disulfiram? Why don't people use it a lot? Because they don't take it. So if the significant other is standing over the person with a baseball bat, then they'll take their Antabuse.
So George, I'm confused about one thing on that. When you go from negative reinforcement back into that warming hut, you're not really in a positive hedonic state. You're not in the
Right.
euphoric state. You're not really up in euphoria. Is that a criteria of negative reinforcement, that you come back to the normal state,
Right.
not to the euphoric state?
Right. Exactly right. Exactly right. So in that commentary that Roy Wise and I have put together, we review in a few sentences the way the field of addiction has progressed. So originally in the 50s, and mind you, I wasn't even active in the 50s, in the 1950s, the argument was that drug addiction was all negative reinforcement, that the only reason people took drugs was to relieve withdrawal. That was thrown out in the 60s and 70s when people discovered that animals will self-administer drugs, and they don't have to be dependent. But in the process of throwing it out, I think a lot of people forgot about the fact that by taking a lot of drugs, you become dependent. And so that's where we're going to go today. But Charlie's absolutely right. I mean, you can take alcohol and enjoy it like you did last night, and you're not going to be dependent, hopefully. And you are not, hopefully, repairing some negative state. Unless you're really shy and the alcohol is helping you disinhibit, but we'll go there later. Okay, so this is the Neurobiology of Addiction a la Koob. This is what I call my life's work slide. This is a slide that Nora and I put together for a review a few years ago. We stole it from Trevor Robbins and Barry Everett, and they stole it from somebody else. So it's obviously an evolving circuitry. Almost everybody's favorite structure is on there. The only difference about this is, and I like to use it for heuristic purposes, but also for instructional purposes, is we color-coded it, and we color-coded it according to the cycles of addiction. So the blue is the binge-intoxication stage, the red is the withdrawal-negative affect stage, and the green is the preoccupation, anticipation, or what we're going to call later the craving stage. And just a couple of important things, but I mean, you don't, even if you're neuroanatomically challenged, you can realize that the blue and the red are deep in the brain, and that the green are on the outside, which means largely cortical structures or allocortical structures. So there is some order to this circuitry, even just with a cursory, you know, sort of look at the surface. Now, the argument is that I'm going to make is that there are a number of neuroadaptations that occur in this brain circuitry that start with the famous one cocaine injection that Anto Bonci published quite some time ago, neuroadaptations you see within the ventral tegmental area and the dopamine system. And they progress all the way, I'm going to argue, to the point that your extended amygdala is lit up like a candle, and you're in a very stressful state. And without alleviating that stressful state, you're completely miserable. So I'm going to extend this neuroadaptation from early changes that occur in the dopamine system, and I'm not going to talk about, to extraordinarily pronounced changes in the brain stress systems that I am going to talk about. But before I get there, I do want to talk about the binge-intoxication stage. I want to remind you all of where we've been and where we've come, and how these data that were generated in animal studies were actually rediscovered in human imaging studies to some extent and have been supported. So why do we argue that this structure that involves the basal ganglia is so critical for drug reward and incentive salience? Well,
Hey, George, could you put a rough time scale on it? Because you're talking about these very early events, and then you're talking about this escalation over a much wider time frame. But so how long does it go? And this relates to our time scales of neuromodulation question. So
okay.
in your previous slide, you know, what would the time span actually be?
Well, the time scale would be the first time you ever smoked crack cocaine, right? Or even maybe snorted a line, although most people can snort a line of cocaine and they recover. But it really, those are the first time you experience a very powerful reinforcer that massively releases dopamine, the neuroadaptations have started. Now, we can readapt our brains back to the normal state, and I'll talk about that in a little bit, after 1 or 2 administrations of the drug. When do you cross the line to addiction? Well, that depends on your makeup, your genetics, how much drug you did in the first place, whether you're doing crack cocaine or snorting lines of it, whether you're smoking cigarettes or chewing tobacco. I mean, all of these things impact. But and there are people in the alcohol field that would argue that there are some people who the first time they drink alcohol become addicted.
Right.
I don't buy that, but they argue that.
But in this diagram where you've labeled, for example, the dorsal striatum, the extended amygdala, I presume that these would probably represent different types of neuromodulatory changes that are being
Right.
set up in the brain. So are these timescales over weeks, months, years, all of the above?
But again, it really depends on the drug, you know, whether you're drinking alcohol. I mean, some people, the little old lady in La Jolla syndrome that I argued about for alcoholism could only kick in their 50s, right? They could have been drinking their whole life, and in their 50s they start to become dependent. On the other hand, somebody who does crack cocaine could be addicted within a week, right? So it really depends on the drug and and the context. And we'll come back to your question. It's a good one.
And there are people that can continue to use these substances and not get addicted?
Sure. I've been drinking alcohol all my life. I don't think I've become addicted yet. I hope I behaved myself last night. I can't remember. But no, absolutely. There are people who can, I mean, where you get into this issue that I find a distasteful word is functional alcoholics, okay? I don't like that word, okay? Yeah. But let's hold that thought. That's a good question. All right, so the basal ganglia. And the key parts of the basal ganglia that are involved and involve early neuroadaptations are the nucleus accumbens, the ventral striatum, that's marked up here, NAC, and then the dorsal striatum where the habits are thought to be engaged. And you'll probably hear more about that as the week progresses. But I had to put this up. So as I've been talking about it at the breaks, I've been challenged by Bill Carlozon to write a review of our long-term animosity, scientific animosity, because we're actually good friends personally with Roy Wise. And when I wrote the review, I put the word incentive salience in, like you're seeing here, for part of the addiction process. And he complained, so we got into it a little bit, and he complained that, you know, I was shortcutting major concepts. So I said, okay, Roy, why don't you define incentive salience your way? And this is what came out. Dominance for cues that guide and motivate drug seeking over cues that guide and motivate the seeking of the more natural pleasures of life. And I thought he did such a good job that I would keep that forever. So I'm not sure we should publish this on your website, this one slide, but I wanted to show you that that's what incentive salience is. So there is a major undertaking in the addiction field to understand how this process takes place. How is it that drugs usurp the reward system, take over the reward system, take over the ability of you to orient only to cues that are associated with the drug? And I'll let other people tell you the details. But what we do know is that drugs of abuse impact all in common on the nucleus accumbens in a major way. They activate the system. I like this diagram particularly of Eric Nestler, who does great diagrams because it illustrates in a kind of conceptual way both the role of opioid peptides as a prominent input to the nucleus accumbens, but also the role of the dopamine system. Now, some of you will, I mean, one of the controversies Roy and I used to have in the old days, and I don't think is there a pointer here? This point? No. But one of the old controversies is he used to antagonize me with great relish by showing a diagram of the reward system and addiction, and it was just a dopamine neuron. That was it. That was his whole talk. And you're going to find people that are going to argue that that the reward system is in series with dopamine, and everything has to go through the dopamine system. My argument is that there's plenty of data to suggest that that's not entirely true, and that's why I particularly like the Nestler diagram. So let me just remind you of where some of this data comes from very quickly. Cocaine, and so I'm going to divide my talks today in talking about stimulants and alcohol. I could talk about opiates, but I'm going to leave that out, and so today is just going to be either stimulants or alcohol to compare and contrast. So if you take and train a rat to self-administer drugs, and since I'm the first speaker, I can go through these kind of rudimentary slides. This is a classic one rat study, okay? So if you have a rat that's got a catheter in the jugular vein and hooked up to self-administered drug tanks. So the rat has a catheter, goes down into the jugular. They live in their home cages in our lab with their buddies. They're not deprived of anything, and they will readily self-administer cocaine, all right? And they like cocaine. So if you've ever done these experiments, you know the rats are in the front of the cage, jumping up and down when it's coke time. They know exactly what time it is of the day that they're going to get their cocaine, and they get very excited about it. They load up in the first bit, and it's very, very titratable. It's very controlled, and there's a lesson for treatment of addiction in this slide as well. But if you lower the dose by half, the animal compensates by taking twice as much. If you double the dose, the animal compensates by taking less. And the same thing would happen at a party with human beings. The only difference is that you might have people cut the cocaine later in the party, but you never have them give more cocaine later in the party. And then the crux to this slide is this piece right here. So this is the same dose, here replicated, but this animal was pre-treated, and this is just to remind you all of where we've been, because this study was done a long, long time ago. But if you pre-treat the animal with a very, very powerful dopamine D1 antagonist, this was Sharing 23390, which never made it to the clinic, and I'll explain why, I think. 20 micrograms per kilogram. I don't know whether you guys realize how low a dose that is, but that was given subcutaneously. Micrograms per kilogram of this D1 antagonist. Look at the animal's behavior and how it's changed. He goes nuts. It's not getting the cocaine response. This is what we call in the business an extinction burst. So the animal is pressing like mad for the cocaine. He's not getting the cocaine, and eventually the drug wears off, and the animal settles back into his regular pattern of behavior. So we know that dopamine is absolutely critical for the reinforcing effects of psychostimulants. I could replicate this slide exactly by putting heroin in the rat's syringe and substituting naltrexone or naloxone for the D1 antagonist. Right? You get exactly the same data. So there are functional systems that are quite important for different drugs of abuse for their acute reinforcing actions, and you can block them. And naltrexone is, in fact, a treatment for opiate addiction, approved by the FDA. It's also a treatment for alcohol addiction.
I have a question about that last experiment.
Yeah.
Right? When it stops pressing, you said the drug wore off. Or did it learn that the lever is just not working anymore?
Well, they don't completely stop pressing because they return to their very regular inter-injection interval. So that's why I would argue that there's no, if we kept giving the drug, they would extinguish. So they'd stop pressing, which is what you're asking. Okay? So this animal is showing this extinction-like burst, but eventually they settle down into regular self-administration again. If we've done experiments in the old days where we've taken out the mesolimbic dopamine system, just removed it completely with 6-hydroxydopamine in the nucleus accumbens. And in those experiments, the animals show the extinction burst, and then they quit. Okay, they just stop. So. What about alcohol? This is a Bruegel. It hangs in the Montreal Museum of Art. It's Peter the Younger's copy of a Peter the Elder, and it shows that even in the Middle Ages, things could get out of hand at the local bar. Right? Can we get rats to drink alcohol? Will they drink alcohol? For you, those of you you're not in the alcohol field or never worked in the alcohol field, you're going, well, of course you can get animals to drink alcohol. Well, 20 or 30 years ago, that wasn't obvious. Rats didn't drink alcohol. Why? Because it was aversive. It had a taste that was aversive, so the animals wouldn't touch it. It took a lot of work for people to realize that you could get animals to drink alcohol excessively, and basically it boils down to one simple fact. You got to overcome the bad taste and the after effects of that bad taste, or the first intoxication. So in the old days, we put them on wine coolers. Nowadays, the Gallo Center re-exhumed a technique where you just throw them in the box overnight with alcohol and they eventually figure it out. But rats will readily drink alcohol. This is a bar-like situation in our lab. They have it access at night. There are 2 levers. One delivers alcohol, one delivers water. They can mix their own drinks. They drink normally. Your average Wistar rat will drink equivalent to what you had last night if you drank a glass or 2 of wine. They kind of average in the 40 to 60 milligram percent. Some don't drink. We don't use them. Maybe we should, but we don't. That's experiments for another time. So generally, when I show you data, as I move through my talks, you'll be seeing rats that are drinking in a 30-minute session. Now try and remember that. These are very short sessions. Again, same thing. Rats are not deprived of anything. They have plenty of food and water. They go back to their home cages and hang out with their buddies. When they come out for their alcohol bar session, they're jumping up and down at the front of the cage because eventually they come to like those sessions. Anthropomorphizing, I don't know whether they like it or not, but they seem excited. And they will generate blood alcohol levels in this 40, 60 milligram percent range. 30-minute sessions, okay?
Is that the I always assumed that there would be some sort of peak of, you know, an average rat would get to a certain alcohol intake, but it looks like they're all over the map there.
Yeah, well, I don't remember the data that were used to generate this. Truthfully, it was 20 years ago, but and at what time point it was taken. But once we stabilize them at their given drinking level, and we select the animals to be at a cutoff, usually somewhere around here in this zone, above 20, they pretty well stay at that level. So each rat kind of takes his own amount of alcohol, whatever seems to fit. But remember, these are 30-minute sessions. So back in those days, we pre-treated the animals with, after they've been stabilized, so this is what I was telling you, they're kind of on average at 20 to 40 presses, which generates the data that you saw on the previous slide. We pre-treated them with a microinjection of a non-lipophilic opiate antagonist. This is like naloxone, but it has a charge on it, so it doesn't really spread very far, and that's why we used it. And it doesn't get into the brain. It's actually a medication now for treatment of constipation associated with opiates. I don't know whether it's marketed in the States, but it's been marketed in Europe. So methylnaloxonium is a charged molecule, doesn't cross the blood-brain barrier, but if you microinject it into the brain, obviously it works, and it sticks in the area that we microinjected. So in this particular case, the two things that are of interest is that we had a dose-dependent reduction in alcohol intake, as has been seen with systemic opiate antagonists for years, but we had it in both the nucleus accumbens and the central nucleus of the amygdala, suggesting that these are sites in the brain that may mediate the acute reinforcing effects of alcohol. And I was really pleased to see this study that was just recently came out a year ago by Howard Fields and Jennifer Mitchell at the Gallo, where they actually imaged the human brain in people that had 2 drinks, after they had 2 drinks. And they used 11 carbon-labeled carfentanil, which I think most of you know is an incredibly potent opiate antagonist. It's 10,000 times more potent than morphine. That's the one, if you stay up at night watching nature videos and you see them shoot a dart at an elephant and the elephant goes crumple, 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 that's the drug they used, all right? And then they clean the nails of the elephant and then he wakes up later and lives happily ever after. Anyway, this is an incredibly powerful opiate agonist, and you can see that when the person was drinking in the nucleus accumbens, there's a decrease in the radioactivity expression. And that means that the theory is the endogenous opioids in the accumbens are displacing the radioactive ligand. You're going to see more of these imaging diagrams as we move through the course. I'm going to show you another one later. But the point is, on both sides of the brain, this is a pretty dramatic effect for an imaging study. And here you can see the actual nucleus accumbens labeled in the human brain. So this, in a sense, is a confirmation of what we saw in the rat many years before, but actually demonstrated in the human brain. And again, supporting the hypothesis, and I'm sure others will talk about this, that there is a prominent role for opioid peptides in the reinforcing effects of drugs of abuse. There's a prominent role for dopamine in the reinforcing effects of drugs of abuse. The weighting of those 2 transmitters depends on the drug you're talking about. Obviously, opiates are bypassing the endogenous opioids and going right to the receptor. And many of you here in this room today can talk better about that than I can. And obviously, dopamine, indirect sympathomimetics are releasing dopamine. Alcohol is probably hitting all of them. Endocannabinoids, it remains to be seen. A lot of work needs to be done on endocannabinoids, and so on and so forth.
So George?
Yeah.
Sorry, do we know what is the relationship between alcohol consumption and endogenous opioid release? Has anyone done that to see if it keeps on increasing to a point and then flattens out, or?
The only thing I can think of is Marcus's study, where he looked at the A118G polymorphism people, and they had a bigger But there was a bigger dopamine response, if I remember correctly, to the alcohol, not so much the opioid peptide. That's a good question. I don't think it's been done.
Would be great.
Yeah.
Yeah, it's kind of odd with dialysis. If you look at opioid peptide release with dialysis.
No, but you could do it with an imaging study if someone wanted to bring the patients back. I don't know, it'd be expensive, but could be.
It sounds like it sounds like a fundamental question, like if you want to establish a relationship between the power of ethanol to release endogenous opioids and to know how that plays into addiction, if we knew that the more you get, the more you release or not, either way would be very interesting to know it.
There is a story. It has holes in it, but there is a story that there's a polymorphism in the mu opiate receptor, the A118G polymorphism in humans, that makes patients respond better to naltrexone in the treatment of alcoholism. Okay, but those same patients also, it's a very actually small part of the population. It's not a very large component of the population, and the other piece to it is that there's a peculiar increased responsiveness in those subjects to opiate analgesics, as I recall. So it's not entirely sure to me. Brigitte may want to speak to the molecular pieces involved in that later on. But there is a story in the clinical literature, and it has to do with alcohol response to naltrexone, and there's a dopamine connection to it, although I don't think anybody, as Anto has alluded to, has explored the opioid peptide connection to it, which has to be in there at some point, because even the dopaminologists would argue that, as you can see here, that the opioid peptides would be impacting in two directions, okay, either in series or parallel. All right, so I didn't want to spend a lot of time on incentive salience. I just wanted to remind you of the rudimentaries of the reward system, the impact of these drugs of abuse. Now, what I tell lay audiences to make an impact, and I usually get a few eyebrows raised at a treatment facility when I mention this, is if you look at the action and go to the literature and look at the amount of dopamine released to a natural reward using microdialysis, or I think there's now the voltometry data is coming out, the amount of dopamine released to a natural reward is generally in the literature with microdialysis around 20 to 40% increase in dopamine in the nucleus accumbens, extracellular levels. But if you let a rat self-administer methamphetamine or cocaine, the increases are around 400%. So I think it's really important that you understand one of the basic components of incentive salience is there's a massive activation of the dopamine system that's contributing to these early neuroadaptations. But it also contributes to the second piece. And that is where I'm going to go next, which is if you keep doing that, the brain changes. And it changes in a very dramatic way within the reward system. So this is my favorite painting coming up. This is Picasso. It's called The Absence Drinker. I've seen it now twice in its actual real form. I saw it recently in London. It was on display, and I saw it in Amsterdam. It belongs to the Hermitage Museum in St. Petersburg, but it travels a lot. But anyway, it's a fantastic painting. Just look at her hand. I think it's fantastic. But absinthe was a drink at the turn of the 18th and the 19th century. There were more absinthe bars in Paris at that time than there are Starbucks in Seattle. It's a very powerful drink in those days. It had very, very high concentrations of alcohol. I've been told that by Pernod, who used to make it. And it also had a stimulant in it called thujone, which is a derivation of oil of wormwood. And it comes from the tree. It's a shrub that grows in Eastern Europe called wormwood. And it's a cage convulsant, so it's a little bit like strychnine. So when people were taking this drug in the old days, they were taking an upper and a downer at the same time. And the point of the painting is they don't look very happy. And in fact, you'll find an absinthe drinker painting for all the Impressionists and Post-Impressionists if you go through the museums. One of my friends, actually, who's a recovered alcoholic and opiate addict, gave me a book called The Absinthe Drinker, so you can have every painting that was ever done. Just for those of you interested, who are none of you, I'm sure, but in any event. This brings me to another conceptual piece, and that is the argument that's been made for a long, long time that when you have a massive release of reward transmitters, there's some kind of payback in the brain. There's some kind of adaptation to that change in the brain. And the adaptation is in the opposite direction. So there's a big words for this, standard pattern of affective dynamics produced by novel and repeated unconditioned stimulus. Or you can make it really simple, what goes up must come down. And Richard Solomon at the University of Pennsylvania argued that when you took heroin, this is his heroin diagram, you got high, so the A state was the hedonic effects of heroin, first time taking it. There was some adaptation to that, and when the heroin wore off, there was what he called the opponent process. And you asked, well, then what happens? You know, what's the time course? Well, if you had one drink of alcohol, the next day you're probably fine. Really no untoward effects. But the argument was that if you keep taking heroin and you become dependent, you lose the A process, you lose that pleasurable effect. And tolerance really does occur in addiction, okay? It's still a DSM-5 criteria. So you lose this pleasurable effect and you gain the B process. And actually there are theoreticians who have argued for many years. One of them was a famous guy in France, Francis Colpert, and then later Jim Woods in the United States, a famous behaviorist, have argued that the B process is actually huge and subtracts out the A process. And I hold to that kind of construct. So maybe you all don't spend your life trying to figure out what causes the B process, but that's what I've been doing. That's what I've been doing for about 15 years. When I wake up in the morning, the first thing I think of is what causes the B process. That's bullshit. But in any event, yeah, you can start in the B process, and that would be pathology that could lead to addiction. It could be your personality, and we can come back to that issue. But the B process is I would argue, is a key process involved in addiction. So you can envision two things that occur that can cause a B process. One, you can, in very simplistic terms, you can think that the reward system becomes compromised. But I'm going to make a second argument, which is that the stress system becomes recruited. And that's something I think that's slowly taking hold in the field and beginning to have an impact, and certainly has tremendous relevance for treatment of addiction. All right, so where do these changes occur? Well, they occur in the same structures I was arguing are part of reward, but now I've colored it differently on purpose. The nucleus accumbens, I'm going to argue, is compromised. And I'm only going to touch on a tiny piece of that part. But I'm going to spend a little more time, I hope, in arguing that there are stress systems in the amygdala that become recruited. All right? And this structure is called the extended amygdala. You'll hear me yabber about it. Not everybody accepts this construct neuroanatomically. It came from Leonard Heimer, whom I knew pretty well because I met him when I was at Walter Reed many, many years ago. And we kept in correspondence, and I loved his work. But his argument was that there are cytoarchitectural similarities in these structures. There's inputs and outputs that are similar in these structures, that they talk to each other, they hold hands together, and that they have a common functional role. Others argue, like Barry Evett or Larry Swanson, if they were here, would probably argue that, well, that's a great idea, but it's baloney. Really, these are just part of corticostriatal loops. It doesn't really matter because both anatomical connections are true, but I still think that there's some heuristic value to labeling this as a common structure. For one thing, as I'm going to argue in a little bit, this structure is marked very well by immunohistochemistry of CRF-containing neurons, just as an example, and immunohistochemistry for CRF terminals. So if you want to mark the central nucleus of the amygdala with a chemical marker and have it throb at you in the histological picture, just use a CRF antibody and you'll see the amygdala light up, right? The central nucleus of the amygdala. All right, so that takes me now to another animal model. And this is one that, that we found serendipitously, actually. It was Serge Ahmed, who was a postdoc with me, that was looking to see if he could prolong extinction from access, with longer access to drugs of abuse. So it was a good example of where we were after A and we found B. And then when we found B, we realized what dunces we'd been for 20 years, all right? And why hadn't we ever looked at this before? And it was right in front of us and we missed it. So those are the kind of things, and that's one of the, for me, that's one of the great joys of working in science, is when you find things that you don't expect and they take you in a completely different direction and they change your life, all right? So the way the experiment ran was that Serge thought that if he gave the rats extended access to cocaine, let them have more cocaine than normal, that would produce a resistance to extinction. But what he wasn't expecting is what happened in between. So the way the experiment was done is rats were, as I just showed you, they had a catheter in the jugular. They were trained to self-administer cocaine for 1 hour a day, or maybe in the original experiment it was 2 hours a day. Fixed ratio 1, they just get 1 infusion for each injection. They had limited access to the drug, no signs of dependence, no signs of changes in their behavior. But then he took another group and he let them have 6 hours access to cocaine after they'd been trained up. Everybody was trained up the same way with 1 or 2 hours access. Then they were split into 2 groups, and one group got 1 hour access and one group got 6 hours access. Now I'm not going to show you the original experiments and all the replication, but I do want to show you that in a later experiment done also in collaboration with Paul Kenny and Athena Marcoux, Paul will be here probably tomorrow, we implanted the rats with electrodes in the medial forebrain bundle, and the animals were trained not only to self-administer cocaine, but before and after each cocaine session they were trained on a threshold procedure for measuring brain stimulation reward. So the way this works is it's very simple actually. It's like a pain threshold, only you could call it a pleasure threshold, that the animals are trained, and if they, so they get this current, 180 microamps. If they respond, they get a free one, all right? If they flick that wheel, they get another one. If they flick, they get a free one again, same thing. So you're probing them with the rewarding stimulation. If they like it and they flick the wheel to get another one, then you get a plus. As you lower the currents, you can see, as you lower the current, you get more and more minuses. Finally, the rat says, well, I'm not feeling anything. I don't care about that stimulation. He doesn't bother to flick the wheel. He goes over and grooms, all right? And then you start over again. You go up, and then you go down, you go up. Anyway, it's a very, very stable response. You're tapping directly into the medial forebrain bundle. And we know that drugs of abuse will lower thresholds for brain stimulation reward, and we know that withdrawal from drugs of abuse raise thresholds. So that means, if you want to put it in simplistic terms, during withdrawal, we've known for years, if we experimentally administer the drug, that animals during withdrawal show increased dysphoria, if you prefer, if you like, but increases in reward thresholds. All right, so increase in reward thresholds means it takes more current to drive your medial forebrain bundle. Something's not working right. So the experiment was as follows. We have rats now who have catheters in their jugular and electrodes in their medial forebrain bundle. The rats are allowed to self-administer cocaine either 1 hour a day or 6 hours a day. The rats are tested for brain stimulation reward thresholds before and after each session. It's an incredibly complicated experiment. The postdocs that did this, like Paul Kenny and Serge Ahmed, it's an amazing feat to have done this study. We've now done it 3 times with 3 different drugs, and here's what you get. Sorry. What you get, focus on the top panel, is that the animals in the 6-hour group escalate their intake of cocaine, and it just keeps going up. If you want to be simple about it, they show tolerance, right? but they also show withdrawal. So as they escalate their intake of cocaine, the reward thresholds before and after each session keep going up in parallel with the escalation. So there's a reward deficit, a reward withdrawal syndrome in parallel with this escalation in intake. Same thing happens for heroin, another study done by Paul Kenny, and more recently we just published the same exact thing for methamphetamine, just graphed in a slightly different way. So we've now seen this phenomenon basically with all major drugs of abuse, which is during withdrawal from excessive drug taking, the reward system is compromised. I don't think there's any other interpretation that you can make out of this other than the animals find that their reward system is challenged during acute withdrawal.
How long does that last?
It depends on the drug. I'll show you data in the second half where you can see with nicotine, ironically enough, that it can last for over a week. For cocaine, it generally lasts about 72 hours. Now, in parallel with this, and this is another conceptual piece that sometimes people have trouble with, but in parallel with this increase in reward thresholds or decreased reward, in parallel with an escalation in intake where the animals are taking more and more drug every day, they work harder for the drug if you challenge them on a progressive ratio schedule. They don't work less hard for the drug, they work harder for the drug. And we've replicated these data. This is every drug of abuse up here. We've replicated these data. We replicate these data on a monthly basis in my laboratory. So they're very reliable phenomena. We use what's called a progressive ratio schedule. What that means is that every time the rat presses for whatever drug it is, we increase the cost on the next reward. So the rat might press the lever once to get heroin. The next time it costs him, he has to press twice to get the same dose. The next time 4 times. The next time 8 times. I should use cocaine as an example. Rats will press like mad for cocaine. You can see here they're pressing up to 200 times for one injection. Not so for heroin. Rats will quit after about 10 or 15 presses for heroin. When you get down to nicotine, it's even less. And that says something about rats and something about their reward system and something about these drugs of abuse. But I'm not going to dwell on that. But I want to emphasize the point that this motivational deficit is pronounced and it's reflected in what I consider this a measure of compulsivity. Not everybody does. You could probably replicate these data, and I know Paul Kenny has done some of this, and I think some of you others have, Anto has done this. You could replicate this with animals where you ask them to respond in the face of punishment. In other words, you make it aversive for them to respond for the cocaine. The animals that have extended access will respond more vigorously. They'll keep pressing for cocaine even though they're getting punished for it.
Can you speak a little to the difference between the long and the short access and what you think is really differentiating these two groups?
Well, what's differentiating them, to be really blunt, is the amount of cocaine they're taking. All right? So that's the major difference, is they're getting 6 times as much cocaine in the extended access. Now, if Piazza was here, we could have one of those fights again. There would be a good fight for future articles. But, Piazza would argue that only certain rats will show this escalation. But that's because of the way he designs those experiments. And all our rats show escalation on cocaine, but that's because of the way we design our experiments. So we give them unlimited access, and we're using Wistar rats who happen to like cocaine, all right? But, you can construct this in such a way as to manipulate the number of animals that are going to show this addiction-like phenotype. For example, if you were to enrich the environment that the animals live in, or you were to restrict the amount of time they could get to the cocaine, you will find that you'll start shifting the curve so that less and less animals will take the drug. Our rats aren't in a rat park where they have access to sexy females and sucrose and all kinds of goodies. But if we were to do that, because I'm sorry, we're only using male rats here, but you could design the experiment in the converse if you wanted to. And Jill Becker has done some really beautiful work if you're interested in female rats doing things to get access to male rats. You have to construct the experiment just the right way because they're picky, but whatever. So my argument is that you can be born that way or you can take a lot of drugs. I'm going to make this argument over and over again. Both contribute to the vulnerability to addiction. And in fact, they probably interact. And you can be abused as a child, and you can live in a crack cocaine neighborhood. And so there's environment, there's genetics, there's a history of stress, and there's how much drug you actually take.
So to follow up on her question a little bit, that 6-hour period of continued exposure, if you were to break that up and separate, so give them, say, 6 one-hour blocks that were separated by...
Yeah, that's a good question. We haven't done that. The person who's come closest to doing that is Dave Roberts. You could look at some of his work, but I think, and there's other binge models that are out there. I think Klaus Mitschik has let animals have 24 hours access. I just saw a paper I reviewed where they've been doing that with, I think, methamphetamine. The problem we had with that, and Roy Wise published this 20 years ago, if you allow rats with cocaine at least 24, 48 hours access, you end up losing about a third of them. We think they have seizures and die, but they suddenly abruptly stop and you find them dead in a cage. And they also abruptly stop in the middle of these. Even if they don't die, you see these big gaps in their responding. So we're not entirely sure. I mean, I've never sat a postdoc in there all night to watch the animals to find out what they're actually dying of. But if I had to guess, with cocaine, I'd say it was probably a seizure. So we've shied away from that really extended access. But you will get a change. You will get similar effects if you allow them continuous access. We settled on 6 hours. I mean, the original paper, one of the original papers Sun Mi published is we got 12-hour access in there, but we lost one of the animals. So we kind of shied away from using anything longer than 6 hours. And 3 hours is a threshold in the other direction. You know, some rats actually will escalate in 3 hours, but they're rare. Yeah.
Isn't the repeated withdrawal an important component of the escalation as well?
Yeah, presumably it is, because absolutely. And that argument has been made even stronger in the alcohol field, okay? Because these systems I'm going to be talking about sensitize with repeated withdrawal. Yeah, good question.
So what George was saying, Matthew, is true. I mean, Roy will tell you that he can design a protocol so that all of them will basically die of a cocaine overdose because of seizure and whatnot. So 100% of them. So it's exactly how you design it that can shape what question you want to answer.
And for the people interested in individual differences, the Piazza model is super because you want that model so that you can dice out perhaps some expression of genes in a specific nucleus someplace that's going to tell you why those animals are more vulnerable. So there's nothing wrong with Piazza's model. I didn't want to put it down. It's just that his interpretation of his model is that it's the only model. But I will not go so far as to say that about my model. But if you want a simple model, you can go with Koob's model, okay? All right, so how do we get there? How do we answer the question that I wake up every morning struggling with? How do we account for the opponent process? So in a galaxy far, far away, a long time ago, Floyd and I, Bloom, actually wrote a paper. I was always eternally grateful for him challenging me to do this paper for many, many reasons. But we wrote this paper and we speculated that there were two ways that the brain could adapt to insult by a drug of abuse. And one would be, we argued, a within-system change, which is, we've kind of argued over the years that this means a change within the reward system. And the other would be a between-system change, which we argued at the time with some other opponent-like process coming in that counteracted the effects of the drug. And we were thinking really of opponent process when we wrote this. And we were thinking that there could be changes in receptors in the opiate system, and I know Chris will probably talk with you about that. that could be a within-system change to opiates, for example. It could be endocytosis, although he poo-pooed that last night, but you know, I still hold that up as a potential possibility of receptors, or how slow they endocytose, or how fast they endocytose, or where they endocytose, or what opiate receptor does and doesn't. Or it could be a circuitry change, and I've tended to focus on the circuitry changes. But I do want to talk about a within circuitry change. So one of the arguments I make, and I think this is borne out very well now by the really beautiful work of Nora Volkoff and her imaging studies, and she'll tell you all about this in great detail. But I'll whet your appetite, so to speak. So the argument is that the reward system becomes compromised, that this system becomes less active. It can become less active here, or in any of the modulatory systems involved, all right? But one of the simplest and most obvious change that we see, and remember I said if you let an animal to take 12 hours access to drug, they take an enormous amount of drug, and you get an enormous amount of release of dopamine, and I might add serotonin. This is an old study. But during withdrawal, those levels fall below baseline. And this has been replicated in many different ways. But this is kind of a dramatic representation. This right-hand side is just a blow-up of this. This is the work of Larry Parsons and Bert Weiss. And then this has become an iconic slide, but I'm going to show it to you because it makes a really important point. I mean, this slide's probably the slide most showed in the addiction field of any slide ever shown. Anyway, so this is a normal control. This is imaging of D2 receptors in the striatum. You can see the striatum, and red is high, so high dopamine D2 binding. This was done by Nora Volkoff. So, and you're going from top to bottom, so across the top of the head like this, all right? And here's a cocaine abuser, 1 month out. You can see that the dopamine system is compromised. There's less D2 receptor binding. And if you look 4 months out, you can see that the red is starting to come back. There's a hint of recovery of the dopamine system. Now, Nora has shown this, and others now, for every major drug of abuse, the same loss of D2 function. And it's been interpreted by Nora, and she gave a beautiful talk at Dopamine 13. I'm assuming you'll get some version of that here. But it's been interpreted by her as actual compromised dopamine function, because when she challenges these individuals with methylphenidate, she sees a blunted response.
So, George, if you had the same tools now to study any receptor you like, CRF and whatnot, do you think you would see 100 of these patterns over time with CRF receptors or with other receptors? What do you think?
Well, I think you'd see, I would hypothesize you would see some change in the CRF system, yeah. And I think if we eventually get the tools, we're going to see that this effect is more dramatic with psychostimulants, whereas maybe the opioid system is going to be more dramatic for opioids. And maybe alcohol is going to titillate all of them. That would be mine, off the top of my head.
George, you said the intracranial self-stimulation comes back in about 72 hours, back to normal.
Right, in the rat.
This is taking, like, yeah, has anyone done this in the rat with the D2? To see if, I mean, I've always thought that would kind of parallel each other, the D2 levels and the ICSS.
Trevor's done a study. There is a couple of studies out there on the D2. And I don't know that anybody's done a time course in the rat. I mean, that's a good question.
Yeah. So
And I mean, people could do it now. It could be done. I don't know. It's PET, but you said PET, Brigitte, it's not very sensitive in rodents at this stage, right? The pixels.
Resolution is pretty low. At the moment. Much better.
George, on the previous slide, you also showed us serotonin. It looked like the serotonin effect was even more robust.
Yeah, yeah.
And it looked like what do you make of that in terms of the contribution to the dark side? That depression in serotonin is really striking.
Yeah, I mean, it hasn't been followed up that much. Larry Parsons worked on the 5-HT 1B system, which each serotonin receptor seems to do something differently, and the 1B seems to facilitate or have a role similar to that of dopamine activation. So it remains to be seen what that means, but if the 1B receptor in the accumbens is part of facilitating the reward function, then you could imagine that that may be having an impact as well, absolutely. I mean, clinically, serotonin reuptake inhibitors have not proven to be very effective in treatment of addiction, although they're used widely by physicians. It's one of the things they throw at patients, kind of indiscriminately. You know, I mean, but I'm old enough to remember when NIDA had 6 desipramine studies ongoing and they all failed. All right, desipramine was a monoamine reuptake inhibitor that blocked norepinephrine and serotonin. So that was its claim to fame back then. And, you know, none of the reuptake inhibitors are really proven to be effective, except, you know, Barbara Mason can tell you about antidepressants work well in depressed alcoholics, and they will treat the depression, and they also help in those patients, that subgroup, they help with the addiction. So maybe the serotonin's contributing to that kind of comorbidity, and there's a pretty good comorbidity depending on which group you're studying in what area. I guess I've just talked my way into the answer.
Hey, George, if you want to break that point.
No, that's okay. I'll just keep slogging unless you guys are falling asleep. I mean, all right, so I zoomed this slide. Oh, yeah.
I just have a comment. So if you go back to Nora's slide, so in terms of in rodents, so I'm in Barry Setlow's lab, and we have this task. It's a risk-taking task, and we see that when we give cocaine to animals, they become elevated risk takers. So they're just going for this large reward. And in animals that are also elevated risk takers, you also see this significant decrease in D2 receptors in the striatum. So it sort of models what we see in humans, if that kind of addresses the question that you asked earlier. We haven't done it like in the same animals, but it's a corollary, if you will.
Yeah, and that's what Robin showed, right? In his impulsive animals, they had a decrease in D2. You just reminded me. Yeah, very good. Yeah.
This might be a little naive, but why the focus on D2, especially in these studies when D1 is the receptor that we focus on?
That's a good question. The answer is because they have a ligand.
Yes. I was going to ask, what is the sensitivity for...
And I never told you why the D1 antagonist didn't work in clinical studies. And they tried it, my understanding is they tried it in schizophrenia. And I think because it was so short-acting, it actually made schizophrenics worse. So my theory is that there was this rebound exacerbation of psychosis when the drug wore off. But they failed in every clinical trial I've ever seen for D1 antagonists. They just failed in the human studies. So I don't know whether they're short-acting or they don't work. And the D1 antagonists have been used in human laboratory studies by Margaret Haney. And I don't know how she interprets the results, but I remember seeing her results. And she was getting exactly the same thing that we get in the rats, which is that the humans were pressing even more vigorously for the cocaine under the influence of the D1 antagonist. And that's one of the problems, all right? And so you can overcome antagonists. That was kind of the lesson that I forgot to mention. When you get into using antagonists for treatment of addiction, with opiates, you could theoretically overcome opiate antagonism. And so the oral administration of the drugs have not worked very well. Now, there's a new preparation out there. I'm not shilling for the Alchemies, but Alchemies has a preparation called Vivitrol, which is being used for treatment of alcoholism. It's naltrexone, long-acting. It's small, fine powder of polymers that is injected into your butt. And it lasts for about a month. And it's pretty hard to overcome that. I mean, some of the drug addicts can find ways to see the window when the release is a little bit less. But be that as it may, once you've committed to what I call the beads in the butt, you're kind of committed to the beads in the butt. So you know, so it probably is much more effective than the old oral administration, which people could overcome, right? With this competitive interaction that you all are picking up on.
It would be nice to have a good D1 analysis. I mean, one of the problems is you don't know if this is occupancy of the receptor or whether it's just downregulation of the receptor.
Yeah, and I heard Chris mumble, and it was Mike Nader who did this beautiful study about 10 years ago now, showing that in primates, again, it fits with your impulsivity issue, in primates at the top of the dominance hierarchy took less cocaine, had more D2 receptors. The poor suckers at the bottom of the dominance hierarchy took a lot of cocaine, were marginalized in the troop, so to speak, and had low D2 receptors, and he could reverse those, that phenotype. All right, I just want to very quickly now remind you of some work I dug out for our sponsors of Dopamine 2013. This is Marco Diana's work, but it's beautiful work actually showing that during alcohol withdrawal, there is compromised release of dopamine, and there's also decreases in firing of VTA dopamine neurons during withdrawal. Now, these were pretty large doses of alcohol, if I remember correctly, probably a liquid diet. But Nora has also beautiful data with alcohol. And this slide is kind of an interesting one because it replicates what I showed you with the previous slide, but it also shows you when you challenge an alcoholic with methylphenidate, they have a blunted response. So you have to go in two directions to interpret the slide. So if you look at the control subjects, when they have a robust dopamine system, and you look at the alcoholic subjects, they have a compromised dopamine system, just like what you saw on the previous slide, okay? So this is the, in a sense, the long-term effects, compromised D2 receptors. But then when she challenges with methylphenidate, the control subjects show the release of dopamine that would displace the ligand, but the alcoholics do not. So this is what she shows now, and again, it's a preview, and I don't want to spend a lot of time on it because you can ask all your questions to Nora, and she's really got a beautiful series of studies now involving cues and all kinds of really exciting things. So to end this piece very quickly, as some of you have already alluded to, it's not just dopamine, okay? There are plenty of players in these neuroadaptations that contribute to the change. But what I would like to argue with you is that the data in rats and the data in humans for chronic high-dose use, I'm not talking about intermittent use, I'm not talking about the early stages of incentive sensitization, I'm not talking about the things that pull you into the crack house initially, I'm talking about the things after you've become, in a sense, addicted, the reward system is compromised, right? And I think there are multiple avenues that this can occur. Now, I want to pass now to my main issue, and I'm going to focus on one aspect of this, and that is the argument that there's another piece to these adaptations that we call the between system adaptations. In other words, other circuits, and we don't know how, all right? I'll warn you ahead of time. I don't know exactly how. Anto has a recent paper I'll show you at the second half, one slide. I'm going to steal one slide from Anto, showing one possible circuitry piece. But we don't know exactly why or how this excessive release of reward transmitters activates the stress system, but we do know that it's activated. I have another part in the second half to give you some of the mechanism. So this is going to be a between system adaptation. It's the same extended amygdala, but now the focus is going to be on the central nucleus of the amygdala. And I'm going to focus today on CRF. Charlie Chafkin will tell you a bit more about dynorphin, I'm sure, because it's one of his passions. And you could argue also norepinephrine has a role in this, not norepinephrine necessarily from the locus coeruleus, but I'm thinking more norepinephrine from the ventral bundle that comes and courses up into regions of the extended amygdala like the bed nucleus stria terminalis. And here's our argument. Our argument is that there's a double whammy going on. You lose your reward system and you gain your stress system. And that this becomes a powerful motivation for negative reinforcement. That's my argument. Now, I'm going to show you some data that I think supports this. But my argument is that you lose your reward system and you gain your stress system. And the player that I'm most interested in, I've spent a large part of my life studying, is CRF. I was there at the Salk Institute when CRF was discovered. It was Wiley Vale's group and with Catherine Riviere and Jean Riviere and Joachim Spies, 1981. Wiley passed away last year, which is just an enormous loss for all of us. I still can't get over it. But what we learned when he discovered CRF, his group, was that CRF not only drives the pituitary adrenal axis, which you all know and everybody knew or hypothesized, but we found out subsequent to its discovery and sequencing that CRF drives the sympathetic nervous system and it drives behavioral responses to stress in the amygdala. And there's been an enormous amount of work in this area supporting this hypothesis. CRF is in all the right places to do this. As I alluded to earlier, CRF marks the extended amygdala in a dramatic way. It's localized in the brainstem to cover the sympathetic responses, and of course, there's a high representation in the paraventricular nucleus to drive the pituitary adrenal axis. What's it like having excess CRF? Well, having injected hundreds of rats with CRF, I'll tell you what it looks like in terms of a rat's behavior pharmacologically. It looks like you've given them an enormous dose of caffeine combined with a benzodiazepine inverse agonist. It's incredibly stressful. I don't know whether any of you have ever heard of a benzodiazepine inverse agonist, but a benzodiazepine inverse agonist has the effects opposite to Valium. It's actually been tested in humans. They gave a drug to some poor volunteer and they published it in a case study in Lancet, and the guy developed the most profound panic reaction you could imagine, right, from taking an inverse agonist. And that's what rats look like when they get the drug, the peptide. And subsequently, we learned that CRF antagonists can reverse behavioral responses to stressors, particularly stress situations that are acute and novel in a situation where the animal has to change its behavior. That's the bottom line. Early on, I had two separate research lines. We were studying CRF and its function, and we were studying addiction. But I had a number of intrepid postdocs over the years, and one of the questions we began to ask is, well, what happens to the CRF system? We began to realize that the rats were stressed during withdrawal, and we asked the question, what happens to the CRF system during withdrawal? We used microdialysis in these series of studies, largely championed by Bert Weiss, but a number of postdocs over the years, and every major drug of abuse, including cannabinoids, during withdrawal, there's an increase in extracellular levels of CRF in the amygdala, right? So this is old data. I'm going fairly rapidly. When we published the data on cannabinoids, it was quite a hoo-ha because at the same time, Di Chiara published a paper showing a release of dopamine in the shell of the accumbens by cannabinoids, and the writer for Science Magazine and wrote this News and Views or some variant on the theme, arguing that, see, the neurobiologists are showing that cannabinoids are addictive, just like other drugs. I was getting hate mail, hate phone calls, scientists from NIH calling me up saying that this was unethical, unscientific, and I couldn't possibly publish data suggesting that marijuana was addictive, and claimed that he had been skiing downhill for years at the Winter Conference on Brain Research stoned. And my thought was, I'm glad I wasn't in front of you, dude. So now I want to pass to alcohol. And I'm going to use alcohol as an example of this between-system neuroadaptation. I'm going to go fairly rapidly because I've already explained all the paradigms. We're back to Bruegel. But here's a slightly different take on what I've already showed you. So remember, I told you to remember that the animals have 30 minutes access a day. One of the critical pieces to these experiments, all this last 20 years of work in our labs, is that the animals have to know that alcohol is rewarding. They have to have learned that alcohol is rewarding. They have to have an experience with alcohol being rewarding. Just like you all had a glass of wine last night, all the rats in the studies I'm going to show you were trained to drink alcohol. They were allowed to drink alcohol. So that's the first part here. Then we made them dependent. And we forced the dependence upon them. Now, truthfully, we could let them drink alcohol till they became dependent. The problem is that that takes about 12 to 18 months. I don't have time for that. I'm too old. I'm not sitting around waiting for my rats to become a kilogram in weight and drink alcohol until they're dependent, all right? So we induce dependence. We've done it in multiple ways. One of the ways is that we allow them ethanol, put them in ethanol vapors, where they breathe ethanol vapor 14 hours a day, and they go off of it 10 hours a day, every day. So we go through repeated withdrawals. The other way is we can put them on a liquid diet, and they drink alcohol in the sole source of calories at night with a pair-fed group and all that good stuff. And if we've had pretty good luck with that. You can also get them up to levels very similar to what we have here. Note that the blood alcohol levels are usually around 200 milligram %. That's equivalent to you drinking about 8 to 12 drinks last night. Okay? It's a lot of alcohol. They do fine under this. It has limited face validity, although truthfully, Olivier George in our lab has now gotten rats to self-administer ethanol vapor. I don't have any slides or data to show you, but the fact is it's not nearly as remote a possibility as we thought that this actually has some reinforcing value even in non-dependent animals. So that's how we do it. And when you then test the animals, what you find is that we get all the things I've been telling you about with drugs of abuse. We get anxiety-like behavior during withdrawal. We get reward threshold deficits. We get increased CRF release in the amygdala, which I just showed you. We get the animals drinking much more alcohol because they drink now during withdrawal. We get increased progressive ratio responding. We get increased, Bert Weiss has shown, increased reinstatement in reinstatement models. So these animals now, just to remind you one more time, they're trained to self-administer 30 minutes a day. They're put in ethanol vapors, and at 2 hours or 6 hours or 10 hours into withdrawal, we allow them to drink alcohol again in this situation. So we put them back in the operant box, and they learn to take alcohol to relieve withdrawal. We're absolutely convinced of that. Okay, here's what the data look like. This is from Scott Edwards, but we replicate this on a weekly basis in the lab. And you can see there's an acquisition curve. The animals learn to take more and more alcohol each day to overcome this withdrawal. But they're drinking enough alcohol here that maintain a blood alcohol level in 30 minutes of around 120, 140 milligram %. It's equivalent to 4, 5, 6 drinks in 30 minutes. When these animals come out of the chambers, the operant chambers, they're pretty mellow, okay? The postdocs will tell you. They're sitting there, okay, it's been a good time, right? These are the kind of blood alcohols they have during withdrawal, before withdrawal and then after. So the blood alcohols don't completely go to bottom at 6 hours, but it's close enough. But it doesn't really matter. It's the delta that's important because that's what drives the seeking behavior. So we can test at 2 hours when the blood alcohol levels are only dropped to here. But alcoholics do the same thing, okay? Alcoholics know when their blood alcohols are going to fall below a certain level. They'll then go to drinking, okay? So it's not unusual. So then we ask the question, we know that CRF is activated in the amygdala. We know that CRF drives some of the anxiety-like behavior associated with alcohol withdrawal. So then we ask the question, can we block this excessive drinking with a CRF antagonist? And obviously, you know what the answer is. So if we do a study, this was a study with a CRF antagonist, a small molecule CRF antagonist, was made at the Scripps Research Institute. It's an analog of a DuPont compound. We've given up on patenting it because it's too close in structure to the DuPont compound. But truthfully, Kim Janda made this molecule. It's actually one of the best CRF antagonists we've ever used. It dose-dependently reverses the excessive drinking. So here's the dependent animals drinking, as I said, 3 times more alcohol than the non-dependent animals. Here are the non-dependent animals. CRF antagonist has no effect in the non-dependent animals. It dose-dependently reverses the excessive drinking in the dependent animal. And again, I always say this, and those of you who heard me talk before, can yawn, but you know, this is a remarkable pattern of behavior that we see here. The CRF antagonist has no effect in the non-dependent animals. We've replicated this 20 times. We've tested 6 different CRF antagonists. But in the dependent animals, this is an extraordinary effect. We're reversing this excessive drinking. And just one second. And we think where it's occurring. And that is probably in the central nucleus of the amygdala, because that's the only spot where the CRF antagonist seems to work when we micro-inject the antagonist. And this was a mixed D1, a mixed CRF1, CRF2 antagonist. And again here, no effect in your non-dependent animals. Yeah.
I'm wondering if the CRF response is specific to acute withdrawal, or is it sustained over, say, like a week or 2 after withdrawal? And the same for the effectiveness of the drug?
Yeah, so it works in protracted abstinence as well. We've done that. Marcus Heilig has replicated that with his colleagues at Lilly. But I didn't put those slides in, but if you look at 2 weeks into withdrawal, you generally have an increase in drinking about twice as much in the animals. And the CRF antagonists block that as well, right? So it blocks protracted abstinence and it blocks acute abstinence. And in fact,
What's the status with, are you going to talk about clinical trials with this kind of compound or translational possibilities?
yeah, I mean, that's one of the big disappointments. So let me finish this slide and then I'll address that question. But basically what I've been arguing here is that CRF increases during withdrawal, and these effects are most dramatic with alcohol in our hands. Withdrawal-like anxiety and aversive responses are reversed by CRF antagonists. We have very little effect on baseline self-administration. There are some binge models where the CRF antagonists actually work, one that's been studied in mice. We see robust decreases in dependence-induced drinking either during acute withdrawal or during protracted abstinence. And then there's a huge amount of work done led by Jane Stewart, Yavin Shaham, Ron C., Bert Weiss, A.D. Lay. All of these individuals have contributed, not me, to this arrow. So what's the status of CRF antagonists in the clinic? Well, it's pretty abysmal, and it's one of the great disappointments. So the bottom line is that they seem to have side effects, and each drug seems to have a different side effect. They either elevate liver enzymes, or they shrivel your testicles, or they cause seizures, and they just haven't been, most of them haven't gotten into phase 2 clinical trials. And the ones that have gotten into phase clinical trials, the trials I'm aware of have failed. Okay, so the indication was depression, and I think anxiety is a secondary, and the Bristol-Myers compounds have not been successful in those indications. Now, if you actually look at the animal literature, I was talking about this last night, I think, the data for CRF antagonists in animal models of depression is not that good, but they should work in some anxiety disorders, in my guess. I just don't know the answer.
But have they been tested in addiction?
No. I mean, there were some trials going on at NIH, but I heard until that they've just been suspended, so I don't know if that's true or not.
There's
Nothing going on. Yeah.
Focusing on the kappa antagonist, right?
Hmm?
The focus on the kappa antagonist.
Well, I'm going to let Charlie tell you about the kappa antagonist, because that's a really exciting area as well, but there are no clinical trials on kappa antagonists either.
I was hoping you expand a little bit more. You're talking about the anxiety state during the withdrawal phase, but also the animals are also experiencing a dysphoria, which may be a different circuit, and they may also be involving a craving element, which may be a cortical circuit. Do you see those as examples of 3 possible circuits? And would you imagine that you could study them separately? And a related question is, when you follow things like using intracranial self-stimulation or breakpoint, do you see the CRF antagonists influencing the motivational state during the withdrawal phase in ways that allow you to separate anxiety, dysphoria, and craving?
Yes and no. Charlie. This is a really good question. I'm going to show, I think, a slide if we get to the second half on that Brunzel has done. But Andre Brunzel, I can never pronounce his name properly, but it's Brunzel. He's done some really nice studies. He's at Florida, University of Florida, and I think in Gainesville. Andre has done some really nice studies looking at brain stimulation reward thresholds during withdrawal and blocking those effects with the CRF antagonist. So he has seen that with alcohol and nicotine, but I'm not sure about cocaine. And that's where I think the distinction may lie, is that with the stimulants, you might get more of a dynorphin dysphoric effect and less of the anxiety effect. On the other hand, the cortical part will come to later. I'm going to table the answer to that later, because we have some data now, just beginning, for CRF. The dynorphin piece is even probably more interesting, but we haven't been working on that. Okay, so this is a kind of an earlier version of what we think is going on in the extended amygdala. You'll notice that I put dynorphin and CRF in parallel here. I'll let, again, Charlie tell you some of the data there, but there is evidence in both directions, dynorphin driving CRF and some evidence, some more stronger evidence actually for, I believe, CRF driving dynorphin. But there may be both going on, in fact, and there may be multiple inputs. The part that I just put this slide up to tell you is that we do have a large electrophysiology group at Scripps in our department, led by now Marissa Roberto, and she has identified a GABAergic interneuron here that CRF impacts on, and there's a very coherent story that's evolving showing that in parallel with what we see, it's a little bit counterintuitive because you think of GABA as inhibitory, but in fact the GABAergic neurons are activated during withdrawal, and they seem to be blocked. You can block that effect with CRF antagonists. So it's a beautiful kind of story that's in parallel with the physiology. To make GABA inhibitory again, all you have to do is add another GABA neuron in there. So it's okay, all right? You know, that's one of the things I love about electrophysiology. If in doubt, just throw in an extra GABA in the neuron.
Yeah, that's right.
That's for you, Anto. But anyway.
I'm pretending not to hear it.
Anyway, here's our overall picture. There's a rich story evolving here. I think it's there's some very exciting possibilities. I have a postdoc right now who's just absolutely persuaded that hypocretin's interfacing with possibly the CRF system. There's certainly, you know, you'll hear about dynorphin. Marcus Heilig has some data. We have some data with him on substance P, the NK1 system. Norepinephrine is kicking around in there. Gary Aston Jones has some beautiful data on opiate dependent animals and norepinephrine in the BNST. And believe it or not, vasopressin is probably a stress-like neurotransmitter and may impact on in the amygdala as well. Old story. The last piece for this lecture is that, what about this piece about addiction as an executive function disorder? Well, I'm not going to speak to this much right now, but I just want to remind you of some global concepts to think about that will certainly filter into the rest of the week. And that is that, you know, to put it in Anna Rose Childress terminology, there's a go system and there's a stop system, all right? And it's pretty tough to get your head around all the functions of the subregions of the frontal cortex in the human. It's even tougher to extrapolate those to the rat and see what corresponds in a rat. But the fact is the dorsal part of the prefrontal cortex probably has more to do with decision-making, engaging habits, activating, planning, thinking ahead. But there's a system in the ventral medial part of the prefrontal cortex that's basically the one that says, don't get off on that exit of the freeway where all the bars are that you used to visit. The problem is, in addiction, that we're beginning to see evidence of compromised function in both parts of the system, that the glutamatergic system has become sensitized in the dorsal part of the prefrontal cortex, and that the inhibitory system is becoming compromised, leading to even more impulsivity. So, as Nora always reminds me, she always says, Koob, The impulsivity doesn't go away in addiction. So some people are more impulsive than others. We've already discussed that a little bit. But unfortunately, taking a lot of drugs can increase that deficit. And especially if you take them during adolescence. And that's a story that's really evolving with marijuana that's getting very, very serious. But here's the argument that escalation in drug intake can lead to frontal cortex abnormalities. I'm going to argue in the second half, if we get through it all, that we think there's some CRF involved in that impairs executive control. There may be some CRF in the ventral tegmental area that's impacting on that, and that can start engaging the system. And so I'm...
Do you think about that as a neurodevelopmental thing or a neurodegenerative thing?
I think it's both. It's neurodevelopmental if you start taking drugs at 12 years old and continue in through adolescence. And all the data, I mean, Denise put a slide, a figure in this chapter I was telling you about, Denise Kandel, and the data are incontrovertible. You have a 2 to 3-fold higher likelihood of becoming substance dependence on a drug if you start the drug at 12 years old than if you started at 21. Cigarette smoking is one of the most dramatic, right? I mean, you look at the data, people just don't start smoking cigarettes after the age of 21. Ask anybody who ever smoked cigarettes and you'll find out that most of them started smoking in adolescence. So, but you can kill your frontal cortex as an adult, all right? And Wernicke-Korsakoff syndrome is the most dramatic example of that. But there are dementias associated with high-dose alcohol use.
That's what I'm wondering with some of these cortical dysfunctions that you're talking about in, say, a chronic alcoholic. Do you think that's actually loss of the neurons that are comprising that circuitry?
Yeah, absolutely. And loss of circuitry. There's some beautiful work by Edie Sullivan, and I need to make a slide of it someday. There's some beautiful, I use this in the lay audience as this example to give them some hope at treatment facilities. But Edie Sullivan and Dolph Pfefferbaum did this beautiful study where they imaged alcoholics performing a go-no-go task. Everybody know what a go-no-go task is? You know, where you have to respond when a certain number comes up, but withhold responding when another number comes up. And of course, you can make it more and more difficult or less difficult. Well, the recovered alcoholics, these were recovered alcoholics, did fine on the go-no-go task, even when they pushed it. But when they imaged their brains, the controls were using a very circumscribed frontal, if I remember correctly, dorsal prefrontal cortex to ultimately cerebellar connection, basal ganglia cerebellar connection. But the recovered alcoholics were using a much more diffuse network. So they had recovered not by growing back the circuitry that they'd lost, but by recruiting other circuitry. It's a pretty elegant series of studies that they've done. Okay, so to end here, take our break. Our argument is that the opponent process continues during the course of addiction. It just keeps getting worse over time. The thresholds fall below baseline. We call this an allostatic change, which means that there's a set point change. It becomes much more unstable. It can lead to pathology, not necessarily, but you're more vulnerable, and you have a much more restricted range of activities. So any stressor comes along to your reward system, you relapse. You may not see it overtly in the organism. They may appear to be fine. I can tell you that any clinician will tell you that 2/3 of relapses occur during states of stress. Just look up the work of Alan Marlatt. And this Barney Carroll actually gave me this. This is a diagram that where the reason the thing is there is because it looks like if you push it with your finger, it's going to fall over. So remember, this is an allostatic, not an allosteric change. So what I've said is all this. The extended access to drugs of abuse are associated with compulsive use. Acute withdrawal from all drugs of abuse produces decreases in dopamine function, increases in stress-like responses. Development of compulsive drug use is associated with dependence, may be mediated by a progressive recruitment of brain stress systems. I'll talk about the HPA axis next time, CRF and the VTA and frontal cortex, but I focus today, right now, on the amygdala. And so the dark side of the neurocircuitry of addiction may involve multiple stages of the addiction cycle to initiate and perpetuate the negative emotional states that drive dependence. So I've already kind of said all this. This is my new diagram. This is the one I put in the commentary with Roy Wise. I don't know whether it's going to be accepted yet, but I put it in there. Roy complained that I short-circuited all the terminology, and so you already got his more expanded definition of incentive salience. And then, you know, I want to acknowledge, you know, I have had a superb group of postdocs over the years, recent years. I mean, this is by no means all of them, but this is probably the last 10 years. And the ones in orange have jobs, so I'm pleased to know. And Scott's got a job too. Scott Edwards, he's going to be going to Louisiana State University in New Orleans. But the rest of them, you know, they're hireable for you faculty out there, starting new places. Hint, hint. Okay, that's it for my first half. And truthfully, I don't even have to give the second half. It's up to you as to how much more Koob you want to listen to, because it's already noon.
It's already noon.
And a lot of good questions. But,
Yeah,
you know, I don't have to do the second half, or I can just show you one piece of it or whatever you want. I'll tell you what's in the second half. We have new data suggesting that the activation of the CRF systems in the amygdala may be driven by glucocorticoids, which is kind of interesting, that I didn't expect. We have data on nicotine dependence with CRF, both in the amygdala and in the ventral tegmental area. And we have some data on binging and alcohol suggesting the recruitment of CRF in the frontal cortex. So I've told you what I would tell you. But I'm very happy to stop at this point.
No, let's have a little break and then
So it's up to
carry
you.
on for a while. 'Cause, I mean, I think we had